Welcome to The Explainer. Today, we're taking a look at a classic physics assignment, but we aren't going to treat it like a chore. Instead, we're framing this as a level-up game. Think of it as a quest, where we're going to conquer the absolute foundational mechanics of the universe. And honestly, by the end of this journey, you're going to have the tools to look at complex physics problems and literally see right through the matrix.
So, let's dive right in. At first glance, this assignment on units, dimensions, and errors just looks like standard coursework. But what we're actually looking at here is a document that hides the ultimate physics cheat code. Mastering these basics, it's absolutely crucial because it's the secret to making sure every other advanced concept you encounter down the road actually makes sense.
Here's our level map for today. We'll start with the mechanics of units, dimensions, and errors. Then we'll hit level 1 with some easy questions, escalate things in level 2 with medium challenges, and finally we'll face the boss fight, level 3's hard questions.
Section 1. Physics. Units, dimensions, and errors. Before we can really play the game, we got to understand the tools of the trade.
The most powerful tool we have in our arsenal is dimensional analysis. I really do like to call this a mathematical cheat code. It's this incredible method used to check equations and derive formulas by breaking literally everything down into base dimensions, specifically mass, which we represent with a capital M, length as L, and time as T. When you treat dimensions like puzzle pieces, it acts as a massive safety net against math typos. Seriously, if your dimensions don't match up, you know for sure your equation is broken before you even type a single number into your calculator. It's exactly the kind of check that prevents a simple typo from crashing a multi-million-dollar rocket or, failing your midterm.
Moving on to level 1, easy questions. Time to get those brains warmed up.
We're starting off nice and simple here to build up some confidence before we hit the much denser math. Level 1 is really just about establishing the ground rules of the physical world. First up, let's talk about speed. Converting 72 kilometers per hour into meters per second is an absolute breeze. You just multiply by 5/18, and it scales seamlessly down to exactly 20 meters per second. Easy, right? Now apply that exact same logic to length. Let's shift 5.6 times 10 to the negative 3 meters into millimeters. Since 1 millimeter is 10 to the negative 3 meters, it beautifully simplifies to just 5.6 millimeters. It's so crucial to see how this scaling works in real terms so we can fluently speak the language of physics.
Now, physics requires us to hold two wildly different scales in our heads at the exact same time, the micro and the macro. For the micro, we need incredible precision. Look at a tiny number like 0.007050. Knowing how to identify exactly 4 significant figures here is absolutely vital for precise lab work. But then, in the very next breath, we flip to the macro, the cosmic scale, where a single parsec is a staggering 3.08 times 10 to the 16th meters. We are dealing with the mind-bending extremes of reality here.
What's really fascinating is how juxtaposing these calculations highlights those extremes. We're sitting there calculating 4 sig figs for a fraction of a fraction, right next to defining a light year as 9.46 times 10 to the 15th meters, right alongside that massive parsec measurement. Grasping this sheer scale is, well, it's what makes physics so awe-inspiring in the first place.
All right, level 2, medium questions.
Congratulate yourself on leveling up. The training wheels are officially off now. We're going to begin applying our mechanics to universal constants and performing actual correctness checks on famous equations.
Take the gravitational constant, g. Its dimensional breakdown is m to the negative 1, L cubed, t to the negative 2. Then compare that to Planck's constant, h, over in the quantum realm, which breaks down into m, L squared, t to the negative 1. By stripping these massive, intimidating concepts down to just mass, length, and time, we make them manageable. They're no longer just scary letters in a textbook. They are highly specific combinations of our base puzzle pieces.
So, let's put those puzzle pieces to work, shall we? We are going to prove the correctness of the very famous kinematic equation, S equals ut plus 1/2 at squared. Step 1. Look at the left-hand side. S is displacement, which is simply length, or L. Step 2. Look at the first term on the right, ut, which is initial velocity times time. Now velocity is length over time, and we multiply that by time. The times completely cancel out, leaving us with, you guessed it, just length, L. Step 3. The second term, 1/2 at squared. Acceleration is length over time squared. Multiply that by times squared, the times cancel out again, and we are left with length L.
And boom, this brilliantly illustrates the true power of dimensional analysis, because the left side equals length, and every single added term on the right side also boils down to length. We can definitively conclude that the equation is dimensionally correct. I mean, you can't add mass to length, just like you can't add apples to oranges, right? Since every piece equals length, the math is completely solid.
Now, another really crucial part of Level 2 is understanding our limits. We never measure anything perfectly in the real world, which brings us to error calculations. If a measurement is 50 plus or minus 0.5 centimeters, simply dividing that error of 0.5 by 50 and multiplying by 100 gives us a clean 1% error margin. But this compounds when we look at relative error for things like density, which is mass over volume. The relative error of density simply equals the relative error of mass plus the relative error of volume. It teaches us that errors stack up, and tracking them is honestly just as important as the measurement itself.
Section 4, Level 3, Hard Questions. Take a deep breath, everybody. These are the ultimate boss fights of the assignment.
Let's see how all this builds into much more complex scenarios. This is the moment where we combine everything we've learned so far, the dimensional analysis, the constants, the error propagation, to solve some really tricky multi-step puzzles.
Here we go. Finding the dimensions for Q equals PV over T gives us pressure times volume divided by temperature, resulting in mL squared T to the negative 2 theta to the negative 1. Notice we've actually added a new dimension here, theta, which stands for temperature. Now consider a puzzle like finding the unknown variables A and B in a time period equation for a pendulum. By balancing the dimensions on both sides, we deduce that A must be exactly 1/2 and B must be negative 1/2. Think about that for a second. We are literally deriving the formula from scratch just by making sure the universe's units balance out. No way, right?
Let's pace ourselves through a velocity equation, v equals at plus bt squared. To keep it dimensionally consistent, a must have the dimensions of acceleration, so that's L t to the negative 2, and b must be L t to the negative 3. Now look at this incredibly intimidating error formula. A equals b c squared over d. Honestly, it looks terrifying, but applying our relative error rules makes it a breeze. The relative error in A is simply the error in B plus twice the error in C, because that exponent just drops down as a multiplier, plus the error in D. It looks incredibly complex at first glance, but the rules governing it are so elegantly simple. So the crucial takeaway here is that we can break down almost anything, which naturally leads us to the ultimate question for this explainer. How do we find the dimensional formula for the universal gas constant, R?
Well, the solution reveals itself right through the ideal gas law. PV equals nRT. We just rearrange it to solve for R, so we get pressure times volume divided by moles times temperature. When we plug in our base dimensions, it simplifies beautifully into m, L squared, T to the negative 2, K to the negative 1, mole to the negative 1. We've successfully expanded our base dimensional alphabet now to include Kelvin for temperature and moles for the amount of substance.
Think of this collection of dimensional formulas as the final loot drop of our game today. This is a consolidated cheat sheet of the universe's secret codes that we've uncovered together. We have the gravitational constant g, dictating the attraction of mass. We have Planck's constant h, governing the incredibly weird quantum realm. And we have the universal gas constant r, bridging energy, temperature, and matter. By breaking these down into m, L, T, K, and moles, you now hold the absolute keys to verifying some of the most profound equations in all of science. Mastering these formulas isn't just about passing a test. It is quite literally the first step to unlocking and understanding the deepest mechanics of reality itself. Keep using that dimensional cheat code, and I'll see you in the next explainer. But it leaves us with one final thought as we log off. Are physical constants just the universe's base code waiting to be debugged?